the theoretical attack becomes very practical in certain cases, and there are lots of Linux distributions. One of them is the OpenWRT. That's a Linux distribution for wireless routers, which implements SSL termination, SSH servers, wireless encryption, but it uses the same kernel. And the same kernel uses the same dev random. But I'm not sure about your wireless router. Mine, which looks like the one in the picture, has no keyboard, no mouse, no hard drive, and unfortunately, no interrupt is implemented. They could implement it, but unfortunately, the current version isn't implementing it. They should. So, if there's, yes?
Is that because you said earlier that only some drivers have the
Exactly.
because drivers use on this device is not the other.
Exactly.
This means radio static, right?
Okay.
Radio static?
No. But after we suggested that and they started discussing it, but right now the stable version, the RC5, I think that's the last stable version, isn't using anything to add interrupt. So there is no entropy. No, they do not do anything. There is a flash operating system, but they do not use it for entropy. The only thing which they use is the uptime, the uptime of the machine to feed the entropy, which isn't good enough. And as someone already asked in the beginning, the Linux saves the state of the pseudo-random number generators between boots. So after you turn off your Linux machine, one of the last things that the operating system is doing is keeping some data from the dev random into a file, and whenever the machine gets up again, this data is fed back into the entropy-based PRNG and is used to get entropy to the state, and that's a good mechanism. But nothing is going. There isn't anything going like that in the OpenWRT, unfortunately. So there isn't any state saving between reboot. So it's very, very easy to predict it. Our attack, just using our analysis, becomes very practical. I didn't want to publish a tool, but we were able to implement it and predict the entire output of the OpenWRT PRNG. And this is right for the last version. You could see that's a screen capture from my router from a couple of days ago. And the last version is White Russian 5. And it can also be mounted remotely. You don't need to get random numbers from the operating system. You can just, if someone wants to implement this attack, you can just get one TCP packet from this machine, sync your simulator, find out the exact state of the OpenWRT, and that's it. You own the next output and the previous outputs of this PRNG, and any security protocol that uses this output is vulnerable. SSL, SSH, S-MIME. One last thing that we did, and that's just the beginning, is we did some kind of starting to do research on the entropy itself, because we believe, and we still need to prove it, that web servers or file systems, machines, will have a unique output for its entropy. It will repeat itself. And we did some measurements right now for running on a 2 weeks server, and we found very, very low entropy. That's the number below the 1.028. That's a very, very low entropy per each event. That's from an idle server, an idle Linux server running just file server operations. We were able to see that the actual entropy is very, very low. And again, that's just the beginning. I do hope that we will be able to find some more results on the behavior of the entropy itself. And again, you can see in the table that these are the upper levels, the upper values of each field, which should have been something like 32 bits, but unfortunately keyboard is 8 bits at most, mouse at most 12 bits, the hard drive at most 3 bits, but if you have, as most of us, single hard drive, that's a fixed value, and interrupt that just 4 bits. Per event. No, just per event. Okay, to conclude, what we found out and presented is the analysis of the Linux PRNG. If you're interested in the details, we also presented a much more detailed paper in the IEEE conference. That's a more mathematical one, and at the end of my talk there is the address of my website. You can download the detailed paper if you are interested to see the exact implementation details. Of course, our analysis is limited. Your own kernel may be different. You may change it. It's open source. Easily changeable. We didn't test our findings on unique machines with multi-CPUs, so it may be different, of course. And because there were so many patches, your exact version may vary, of course. Attacks, I mentioned one theoretic, some measurements, very simple denial of service, which hopefully will be fixed in the coming kernel versions. And you can see in the picture, that's the OpenWRT from inside. That's when you need to do hard reset. There's some way to open and use the flash for hard reset when you build the wrong version for the kernel. And unfortunately, that's vulnerable today. And hopefully they will fix it. As someone mentioned, it's quite easy. They should add more entropy to the system. So fixing that's definitely a good step. Implementing the quota. If you are implementing a new entropy-based PRNG, as I suggested, do implement the Baraka-Levy construction. It's very simple to do so. And unfortunately, and as I said, I have nothing against open source, but I do think that open source can do much better for security. And saying that you can read the source isn't the solution. For example, going for different documentation system. The fact that anyone can add changes to the kernel, there is some signing mechanism, but the signing mechanism doesn't prove today any quality. There is no QA, there is no test vectors for any security part of the kernel that I know of. We have similar things for other protocols in cryptography, for example, and in security. We have test vectors for SHA-1, for ND5. Why can't we have some good examples for such protocols in the kernel. And I think that that's definitely a good direction which open source can benefit from that. As I mentioned, you can find, I'll put the latest version of this presentation online. The one on the CD-ROM is a bit different. I added some slides, and you can find a detailed mathematical paper about our analysis on my web page, and I'll be happy to take any questions. No, we have. If you use we want all of them. Actually, we want to make sure that someone who gets random bits from a PRNG won't be able to predict the state. We want to make sure that once you break into the PRNG, you won't be able to know the past, and your ability to predict the future will be very limited till there is enough entropy. So we want all of them, and for the OpenWRT, you don't get any of them. For general Linux system, we were able to show that once you break in, you can predict the past. You can not predict the past, but you can learn about the past, and that's very bad. Think about banking system. Would you like that someone who breaks into the system can learn something about yesterday? Usually not, and it's true also for any commercial system. If the nonce is fixed, it won't be secured as well. Usually they take the nonce also for some kind of PRNG. Yes, please. Mm-hmm. Yes. Yeah, they'll pass it. And by the way, it's a good issue that you raised. The fact that we do have some statistical measurements for pseudo-random number generators, but unfortunately they can only prove that something passes them, but it's not proving anything about its security, of course. Yes, please. As I mentioned, in some systems, yes, and some systems, no. Exactly. I think that the last time I checked, if I'm not wrong, for example, the Intel card and the 3-Chrome cards were without interrupts. So, yes, please.